Okay, the goal today is to finish relativity and then to start in with quantum mechanics. So we'll see if we get finished with relativity and started in with quantum mechanics. So last class period, we were working on the velocity addition. And I know that I and Trace invited other classmates to come join us to finish it out, and they didn't come. So last class period, what we figured out was how to find ux prime in terms of ux and time. I think that was what we did, wasn't it? Or no, we did the other way around. I think we did it like that. And so now what I want to do is have you find uy in terms of now I got to think about this more carefully. Which way did we do it? No, we did the way I wrote first. So I want you to find uy prime in terms of uy and t. So before you get started, each of you working on this yourselves, what was the method we used before? What was the method we used last week? Okay, well,
once we have the function,
we took the definition that ux prime is equal to dx prime dt prime, and so we substituted d of gamma times x minus vt d of with the recollection that gamma and v are constants. Now, both of those were, not with respect to anything, and so we added in with respect to dt for both of them. And then we were done. So now I want you to apply that same technique to find uy prime equals. And there you can see everything you need.
Okay, and then go on to the next step.
That's correct.
This is not y prime. If you look up there, what is y prime equal to?
Y prime is equal to dy over dt.
No, it says y prime.
Y prime equals y.
Yes, that's how we have inside this.
No. Okay. And then u prime is equal to.
T prime is way. Yeah, T prime should be way around. And then continue on with the calculus.
Yeah, is it integrating or drive?
It's derivatives.
Okay, cool. Oh yeah, the,
You can question it.
I just realized they did it wrong.
What?
See what's going on.
Oh, you did it wrong.
Yeah.
So, they said I did. I was like, what? Divide your side. This one, it's right what you here. It's the same. It's T prime. So T prime is that top right equation.
the quotient is that if you
So
just choose it, do it.
yes, choose
Oh.
So again, let's see what else is well, you substitute, so I'm not going to do your two. So what is dt? C, C, constant C, so dx dt plus dx dt.
did just read. Not most. Yeah. And so the top is just. That's the definition of the change in T with respect to T. As T changes, T changes. So you just have one minus. Now V, C are constants. So we have dx dt. So let's dx dt. X. So for constants. And then that's it. Okay. That's true. This is actually
The B.
yes.
Okay, so everybody has completed it now. Obviously, doing it on your own is a little harder than me doing it, but it forces you to realize what we're doing here, that we're just simply substituting in. So you found uy prime. It wasn't actually just of uy and t, was it? What was it a function of? You have three things in it. What are the three things? Not the constants. You all have the answer. Go ahead. Ux.
So they aren't constants.
The things that aren't constants are the things I'm looking for. In other words, not V, C, or gamma. What are the other things in there that aren't V, C, and gamma?
T.
Okay, T. There's one more. Uy. So we had uy prime as a function of ux, uy, and t. So it's a little more complicated. Just to go through the steps so, like somebody watched on the internet, they can see it. dt of gamma t minus x v over c squared. But dy dt was just u sub y, so the top is just u sub y. Then the bottom gamma is a constant, parenthesis, dt dt, by definition, that's a 1, minus v and c are constants, and so I just have dx dt, but dx dt, that's ux, and so there's our equation for velocity addition perpendicular. Now that doesn't look like the Lorentz form. If you were to do it with the, or the Lorentz form, the Galilean method. If you were to use the Galilean method, you would have used the Pythagorean theorem, right? This is a little more complicated, but we now have the way we can add both parallel and perpendicular velocities. And nobody ever does uz prime because it would be identical to uy prime except you change the y to a z. So if you can do the uy prime, you can do the uz prime. So any questions about how we did this calculation? To me, it's really cool because I can take what seemed like some pretty esoteric work from last week and put it into something that actually has good utility. Good utility if you're doing things that have to do with very fast moving objects. So if you're into astronomy. So here are the complete set of equations for transforming velocities. And we'll just move forward from there. So a fun problem. I threw this in at the last minute. I used to do this every year in my general physics class, take an entire lecture on it. It's really fun and interesting and confusing. It was one of the things that on teacher evaluation students like the most, though. So, thinking about rubber meets the road, what happens with relativity? So I have a problem here. I embellished a little. Broomhilda, you guys know who Broomhilda is, the comic strip. She's riding along on her supercharged broom around the countryside. She measures the length of her broom to be 75 meters long. Is that a contracted length or a proper length? She's sitting on the broom. She measures from the front of the broom there to the back of the broom there, 75 meters. Is that proper length or is that a contracted length? Proper. Proper is correct. It's proper because the object wasn't moving with respect to her reference frame. So I'm going to call that L, and so I'm going to write down here so that's the length of the broom. So she's cruising along and she sees Farmer Brown's barn. And she's all, oh, this is going to be fun. I'm going to go through the barn. And so the barn has magic doors. The reason for the magic doors is to help us face the confusion. So she goes for it. She dives down. She goes through the barn. As soon as the front of her broom gets to the barn's front door, it opens. And she goes in. As soon as the front of her broom gets to the back of the barn, that door opens. And of course, when the back of her broom gets to the front, it closes and so on. And so she goes through the barn. Now, Farmer Brown, he's out standing in his field. And he has measured his barn reliably to be 50 meters long. Is that a proper length or a contracted length?
It's proper.
It's proper, right. And so I'm going to put B0 for the length of the barn. And so Farmer Brown sees her going through. And now we have a little bit of a fun question. Does Broomhilda's broom fit completely within the barn?
It depends on what speed she
Yeah.
It depends on what speed. Oh, I didn't write it down. I did. She's going 0.866 times the speed of light. I, of course, did these calculations carefully, but I forgot to write that down. So thank you. V equals 0.866 times the speed of light. Okay, so if V is 0.866 times speed of light, you might wonder, why did he choose that? Because that makes gamma equal to 2. So gamma is 2. Does she fit inside the barn? Does the broom fit inside the barn? So here's the broom. Broomhilda measures it to be 75 meters long. Here is the barn. Farmer Brown measures it to be 50 meters long. Does she fit inside?
I guess yes. Like not
Okay.
realistically.
We have a guess of yes and we have a guess of no. What the other two?
I would say yes.
Yes. What do you
It's
say?
pretty close to the speed of light, but the only way we can find out is if we calculate.
Okay, the other way we can know for sure is if we calculate.
Yes, or
So-
no calculate.
So,
The length.
go ahead, Nick.
Seems like the length relative to the barn guy would be twice as long. Right.
Well, not twice as long, half as long. Remember, it's length contraction.
All right.
So in Farmer John's reference frame, Farmer John says the contracted length of the broom is equal to 37.5 meters. And the length of the barn is 50 meters. Does it fit inside? Yeah, it does. So if you're Farmer John, Chad is Farmer John, yep, it fits inside. Now what about Broomhilda? What does she see? What's the length of the broom that Broomhilda sees? 75 meters, it was already stated. What's the length of the barn that Broomhilda sees?
Half of the length of the boom.
Okay, so she sees a 75 meter broom and a 25 meter barn. She's going to see that there's no way in God's green earth she fits inside this barn. She was 1/3 in front, 1/3 behind, and 1/3 inside the barn all at the same time. Did not fit inside. Now remember, we have the magic doors. According to Farmer John, the front door opened, then the front door closed, then the rear door opened. She was completely contained. But according to her, the front door opened, the rear door opened, then the front door closed. She was never completely contained. How do we make this work in our brains?
Only one of them is correct because of the reference point.
Relativity says they're both correct. Relativity says that, that any inertial reference point is making, well, actually any reference frame, but special relativity, we don't talk about inertial, is making correct measurements, but they're different measurements.
So does the broom get destroyed?
Just the broom gets destroyed. This broom is causing me stress, it gets destroyed. The difference is they don't agree on the times. And so what I was doing, I decided not to do it here. But I went through and used our 4-vector calculations to calculate the time when Broomhilda sees the front door opening, the rear door opening, the front door closing, and the times when Farmer John does. And the problem is they don't agree on what's simultaneous. They're like, no, you measured this, and then you waited until after that happened before you measured instead of measuring when it happened. So they don't agree on the timing. So they're both correct, but they both say, you just didn't time it right. Now, just a few other things that are kind of cool. So we talked about, if I am traveling like this, in what direction is my length contracted? Okay, that's right, in the direction that I am traveling. So if I have a meter stick, and the meter stick is at an angle like this and traveling like this, what's going to happen?
Angled like this when you travel in this way.
Yeah. And so what's going to happen to, when you view it, how's it going to look? Which direction is it contracted?
It's going to be squashed.
Yeah.
And so it's going to be like it's shorter and at a steeper angle, right? So things that are rectangular in one reference frame aren't rectangular in another reference frame. And so you have all kinds of things that change as it trickle down. Now you can do the math, we're not going to do the math. If you have a sphere stays a sphere. Because you have the time it takes for light to go from here to there, combined with the shortening that makes it so it still is a sphere. So you're going to see a sphere at any speed, which is kind of cool. All right. That wasn't... Yeah. Okay, I don't know what happened. I was going to go through and do 4-vector calculations on this, but we won't. Last thing on relativity is the calculation that I showed them in class yesterday, how we go from Newton's second law. What is Newton's second law in its most correct form? Net force equals,
Times acceleration.
it's what?
Mass times acceleration.
No.
That's the.
That's its least correct form. It's a correct form, but it's least correct form. Go ahead, Michael.
Oh, no, it's some equation for that.
Some equation. That's a good one.
Some of the forces.
Sum of the forces is equal to the most correct, it's a derivative. What's a derivative of?
The derivative of
Momentum with respect to time. That's the most correct form of Newton's second law. It's the only one that applies with relativity. Now, for people without calculus, we put delta P over delta T rather than dP dt. It's fundamentally the same thing. The difference is D is infinitesimal. I don't know why my boy wants that, but D is infinitesimal change, whereas delta is a finite change. That's the only difference. So using that as a starting point, then we take the fact of the work-energy relationship. The change kinetic energy is defined as the net work. And the net work is the integral of force dot dx. So we put integral of force, and this should, I made a mistake here, that should be net force because it was the net work, right? But according to Newton's second law, net force is identically dP dt. So I have dP dt dot dx. And now we start doing fun calculus things. Things that, I mean, technically it's not right, but in practice it's right. We can move that dt over from being under the dp to being under the dx. It's still a change with respect to time. But if we do dx dt, we have another name for dx dt. What do we call dx dt?
velocity.
Velocity. And so we then can put dp dot v. Well, this is relativity, but we still have the direction of momentum is the same as the direction of velocity. So the dot product now disappears because they're parallel. And P is gamma mv. So this here is dP. Now V, dP. Well, now we've got integral, and it would look simple except for one thing. Gamma is a function of V. Gamma is not constant. And so I have to expand. And so what I've done here is, and you don't really see the work between here and here, do you? I mean, it looks kind of magical. So let's do that. What was that name?
I suppose I sort of do, because I guess the parallel component, like, they're parallel to each other. It's time.
So there I replaced, my V and my square root look a lot alike, don't they? I replaced the gamma with 1 over square root of 1 minus V squared over C squared. I could probably simplify this a little. I don't know if it's the right thing to do. I'm doing that so I don't have to use the quotient rule. Right? So I'm going to write this one last way to make it still simpler for us to do the actual math. Okay, I do have to use the chain rule. What's the derivative of something to the minus 1/2 power?
And to the negative 3/2 power.
Okay, I have to bring down the minus 1/2, so I'm going to have minus 1/2, and then I'm going to have that thing to the minus 3/2. And then what's the final step?
Derivative of the inside.
Derivative of the inside. So the derivative of 1 over v squared, or v to the minus 2, is going to be minus 2 times v to the minus 3. Now, if we look at this, the minuses cancel, the 2's cancel, and I forgot to write my last thing. There's still a dv here. Whoops, come on, come back. Baby, come back. Thank you. So this is equal to m times that cubed times that cubed, or bringing these, oh, and then dv, don't forget the dv, bringing those together, that's equal to m times and what is that thing in parentheses? Gamma. And so m gamma cubed then, because I had the cube there. So there we have the gamma cubed m, just in case you, where's that v come from? That's this one. That was out front. I wasn't dealing with that. So we have gamma cubed mv dv, and then we do the integral of that beast. Look, we still have gamma in there. I'm not going to do that last integral, but it comes out when you do the integral, you basically undo what you did, and you get gamma final mc squared minus gamma initial mc squared. So, right, we just showed that in class yesterday. Here we can see more of the complexity of how it's done. You know, no one in class yesterday saw it as anything complex. It's just like, sure, a couple equations, no big deal. we still skipped one of the two big deals that were involved. That's my last thing for you guys on relativity. So any relativity questions before we move to quantum mechanics? Trey says no. Okay, go ahead.
Not really, just a question. Why don't we think anything can go faster than the speed of light?
Okay, why don't we think anything can go faster than the speed of light? We can use the same logic that I used yesterday in class. If something were to go fast at the speed of light, gamma would be infinite, and so it would have to have infinite energy. Or we can actually use things like the equation for force. The net force is dp dt, right? And so as speed increases, since p is gamma mv, as speed increases, gamma is getting bigger and bigger and bigger. And if you want to accelerate something, you have to put a force on it, right? And then its momentum is going to increase. But because momentum is gamma mv, momentum is approaching infinity as the speed approaches the speed of light. And so that would mean you would have to apply an infinite force to get it moving any faster. And since we can't apply an infinite force, we're never going to be able to get past that infinite momentum point. It starts getting ridiculous when you start thinking about that and you realize, yes, that just can't happen.
Remember, you can't have mass.
If something has no mass, well, then you don't have that problem, right? Or, just because you brought it up, what if something has an imaginary mass? If something has an imaginary mass, then if your gamma is also imaginary, you're going to have a real value for things like momentum and energy. So how do you get an imaginary gamma?
Take positive square root negative.
Square root of a negative value, which means that you would have to have V bigger than C. So if the speed is bigger than C, and you have something with imaginary mass, then you're back in business. Now, if something has imaginary mass, what speed would give it the lowest possible energy? Remember, you can't have a speed less than the speed of light and have imaginary mass. What would give it zero energy? When would gamma mc squared be zero?
Speed is the same as.
No, then gamma mc squared is maximum because it's infinite.
So speed is infinite?
At infinite speed, it would have no energy. We have a name for these particles. Imaginary mass, speed greater than the speed of light. We call them tachyons. Tachy means fast. So these are fast particles, travel faster than the speed of light. And now, do tachyons exist? I assume no. But if they do, we can't measure them. But these tachyons would have some great properties. The tachyons traveling faster than the speed of light, they could go backward in time. Right? We can't go backward in time, but tachyons can. And so one of my professors said that when he was at his I don't know if it was undergrad or graduate, they had a physics newspaper, and they call it the Daily Tachyon, the news before it happens. Because they're using tachyons to tell you what's going to happen in the future. Now, in case you're worried,
How's it go back in time?
how does it go back in time? Well, you know how we have the warping of the space-time continuum, and as things go faster and faster, you have the time dilation, so that if we said if light is going at the speed of light, no time is passing for that light. If you have something going faster than the speed of light, time runs backward. Yes, the key to making a time machine. But people have done the calculation. You could, in theory, if we could interact with tachyons, I could send a message to Chad that says, "Hey Chad, tomorrow we're going to have a test." And it would get to him before I sent it. But it would be impossible for him to then communicate back to me, "Okay, I'll be ready," before I had sent him the message. You can't zigzag back in time. The forward and backward process is always going to be a positive time. Or to put it another way, by the time he comes to the test, it doesn't really help you out much. You can't say, "Watch out for the attack of Geronimo," and then him get it and say, "Oh yes, I'll be ready," before the attack occurs. Yeah.
So does that mean that if you had sent that message and you sent one back, it could come back to you the moment after you sent it?
Theoretically, yeah, you come back the moment after. But. So, and those are just fun calculations, right? They're not anything that I think has any meaning. All right.
What does imaginary mass mean?
I don't know. Okay, we do have more than one type of electric charge. We do have more than one type of magnetic charge. We have more than one type of color charge. We have 3 types of color charge, which is why they're called color: red, green, and blue, to go with 3 types of cones. So it would just be a different type of mass, different charge. But like I said, I doubt it exists, but who could say? It's theoretical and it's fun to talk about. Like Einstein-Rosen bridges, also known as wormholes. Theoretically, they can exist. Theoretically, you go in here and you come out there at a different time in a different place. Practice, not known to.
You would die.
Well, there's also that, but I mean, we've seen enough Sliders, Stargate, that one with Jodie Foster, to know that there's got to be a way in Hollywood to make you survive. Or, yeah, Interstellar. Okay, particle in the box. We're getting to quantum mechanics. Particle in the box problem. Y'all look at Chad. Say, Chad, can you do this? Yes, he can. So if you need help with this kind of stuff, Chad's your man. Now, we're going to start in on what quantum mechanics is, what quantum physics is. So quantum, that's not where I wanted to. Okay. Wow. I had a whole bunch of slides that apparently I did not include here on what quantum mechanics is. Actually, I think we'll have them at the beginning of labs when I'll have those. So we'll just talk about what quantum mechanics here is because I didn't put those slides in this presentation. So quantum mechanics. Chad, I know I'm totally putting you on the spot. To you, now that you are 2/3 of the way through with the class, what does quantum mechanics fundamentally deal with? Not what does it mean? It means pain and torture. But what is it fundamentally dealing with?
A lot of complicated equations.
A lot of complicated equations.
The quantization of energy in systems that classical mechanics apply to.
Okay, now there is a good practical outcome. So quantum physics started because people really couldn't explain what was going on inside the atom. And you had Heisenberg, who was trying to figure out where's the electron, how fast is it moving, and he's like, I can't figure out where it is. I just can't. And so finally he kind of threw up his hand and said, well, let's look at what I can measure, the observables as we call them. And so I can measure things like its magnetic moment, what we call its spin. Or I can measure its angular momentum, and things like that. And so he focused on what he could measure and started just categorizing them. And then he didn't know what to do with these, passed them on to the other guys. Like, I don't know, this looks like some kind of crazy math. Let me check in with the math guy. And that guy's like, oh yeah, you just do, matrix calculations here. And they came up with a method of dealing with the things you can observe about a system that was outside of what we could classically do. The other approach, we'll learn about Louis de Broglie in his presentation. He said, if light can be a wave or a particle, what we're going to learn about in lab in a few hours, then shouldn't other things? And so shouldn't an electron, something that we think of as a particle, be something that we could treat as a wave as well? And then Erwin Schrödinger gave a presentation on this at a college. I think he was just faculty there, gave a talk about it, the latest advances. And then I think it's Peter Debye said, well, if you're going to be able to treat the electron as a wave, then shouldn't you have a wave equation? And Schrödinger said, yeah. And so he went off and spent some time, and he came up with this wave equation, which is just an energy balance. What his wave equation says is the kinetic energy plus the potential energy is equal to the total energy. But it's written with a whole bunch of fun math. And totally fun. Like I said, just ask Chad. He has all kinds of giggles and grins from this class. So we have the Schrödinger equation. That's a wave equation. From this, we can find a wave function that tells us all the information we need to know, specifically about energy, but it tells us a lot of other things too. Now, quantum, and Chad got into that with his description. Quantum means we're dealing with quantized amounts. Quantized amounts, here's a good example of quantized amounts. The number of students in this class. There could be 0, there could be 1, there could be 2, there could be 3, there could be 4, there could be more. But there cannot be 2.3579268. Right? You come as discrete individuals, not a continuous slurry. We cut it off here, and we have fractional people, right? So that's what it means for something to be quantized. So the kind of results that Chad is finding in his class is we're finding quantized energies. So we are right at the point in his class of finding quantized energies for electrons in the hydrogen atom. There's only certain energies they can have. And so that's the kind of thing we're looking for. The reason Chad is taking class is because he's a chemistry major. Chemistry relies on quantum mechanics. That is the underlying principle to all of chemistry. And so that's why they have to take it, so they can have some understanding of where does this come from, and why do we have to learn N, L, M, M sub L, and M sub S. You haven't gotten to M sub S yet. Why do we have to learn these different things? And Chad has seen why we have N, L, and M now. M sub L again. And when we get to M sub S, we'll be using the Heisenberg stuff instead of, it's fun.
I just like the Heisenberg method.
I do too. Okay, so the first thing here, and I know you're not going to remember or be able to reproduce this, but we separate this equation. Notice this equation has, what kind of derivative is this? Time, but which partial derivative with respect to time? This one here, partial derivative with respect to position. So we have two variables and we have partial derivatives. It's a lot harder with two variable calculus than one variable calculus. And so one of the first things we do is we try to separate the spatial, that's x, or if it's three-dimensional, x, y, z, or r, theta, phi, from the temporal, the time. And so we can do this if we say that our wave function is the product of a spatial wave function times a temporal wave function. We can always do this if, and only if, our potential energy function is only a function of position. If it's a function of position and time, it's not going to work. Actually, I suppose if it was only a function of time, it would work as well. But our potential energy functions usually are just based on position, right? Potential energy is the result of configuration. And so usually that works out. And so when you go through and do that, it breaks up into two equations. Here is our time-independent Schrodinger equation, the one that Chad spends all day long with. And then we have the time-dependent. This is only the time dependence. And this has a real simple solution. We've done this a lot of times. How would you solve this to find phi as a function of time? And this does go back to our first class, the first Tuesday of first semester. I have two variables, phi and time. So what do I have to do to solve for phi as a function of time? Separate variables. So I'm going to take this and put d phi on the left side. And I'm going to have to divide by phi to get the phi away from the right side. D phi over phi. Multiply across the dt divided by IH. IH bar actually is what we call that. It's Planck's reduced constant. Now you integrate both sides independently because the left side only depends on phi and the right side only depends on t. And so when you integrate those, you get that's what you get for that solution. It's a very simple solution that's going to work every time. Now, it depends on the energy. And so if you have a different energy, you're going to have a different rate of precession. I say a rate of precession. Where in the world does that come from? Euler's relation. Euler's relation may or may not be familiar to you, and it's not really important for you at this point. E to the IA is equal to cosine A plus I sine A. And so since that has an I in the exponent, it's sinusoidal. Okay, I just looked at the time and I am out of time. So we will stop there with our introduction to the Schrodinger equation. We haven't done the particle in the box. But we will so soon. By the way, this here is showing the work I just did. So we will start next class period by looking at the results to this calculation.